These are the answers to the crude oil exam questions for the foundation tier. So crude oil is a mixture of hydrocarbons. The hydrocarbons in crude oil are separated into fractions by something called fractional distillation. Figure 1 shows a fractional distillation column, okay? Crude oil going in, being heated up, and then obviously the gas is coming out as liquids here. Crude oil vapour passes up the column, complete the sentence, choose the answer from the box, okay? So each fraction, it condenses, which means changes from a gas to a liquid at a different level, okay? So why do the fractions separate? It's because the fractions have different boiling points, okay? There is a temperature gradient in the fractional column, so the gases condense based on their boiling points, okay? Next question. Most of the hydrocarbons in crude oil are alkanes. Figure 2 represents an alkane molecule. Name this alkane. Well, it's got the black molymods are carbon atoms. So therefore, there are 3 carbon atoms. This means it is propane. Okay. Methane if it's 1 carbon atom. Ethane if it's 2. Propane, butane, pentane, etc. Because it's an alkane, it's propane. Next one, the general formula for alkanes. Whatever the number of carbons you've got, you times this number by 2 and add 2. So that's the formula there. Alkanes burn in oxygen in combustion. Balance the equation for methane burning. Okay, so over here we can see, if we look at as oxygens, over here we've got 3 oxygens, and over here we've only got 2. Now 2 and 3 obviously are even and odd numbers, so what we need to do, balance up the oxygens. So if we do this and put a 2 here, that means now we've got 4 oxygens, okay, on this side. So we've got 4 times oxygens on this side. And over here, we've got 2 oxygens here, we've got 1 here. We can't change the little number, but we can change the big number. So if we put a 2 here, we've now got 2 oxygens here and 2 here. So that means we've got 4 on this side. And over here, now what that's meant is we've actually got 2 hydrogens times 2, so that's 4 hydrogens, and that's right over here. So 4 hydrogens, that's fine. 1 carbon, it's now balanced. So 2 and 2, don't be put off by these, thinking you've got to put numbers in here. You don't always have to put a number there. Sometimes they give you the space, sometimes they don't, but just think about how many atoms have you got on this side, how many atoms have you got on this side, and make sure you've got the same on both sides. So ethene is an alkene. What reagent is used to test for alkenes? It's bromine water, because bromine water turns colourless when alkenes react with it. Next one, the table below shows data from a life cycle assessment for the disposal of 10,000 biodegradable plastic bags. So why are life cycle assessments or an LCA done? It's to assess the environmental impact at each stage of making the product. Okay, so it's to assess the environmental impact that making the product has on the environment. Compare the two methods for the disposal of biodegradable plastic bags. Use the information from the table above. All right, so we're using the information here like we did in the Lady Mabel Hall session. So use the information from the table above. So firstly, the mass of carbon dioxide produced in kilograms Okay, so burning it produces 25 kilograms and landfills produces 15 kilograms. So burning 10,000 bags produces 10 kilograms more of carbon dioxide. However, if we see here, the mass of the solid residue when we burn it is 0.05, but in landfill it's 0.07. So putting 10,000 bags in landfill produces 0.02 kilograms more of solid residue. We're just comparing here, we're not evaluating, okay? So you don't need to say which is the best, you're just comparing. More of solid residue and also put in 10,000 bags in landfill or landfills produces 50% more sulfur dioxide than burning, because 0.2 kilograms of sulfur dioxide is produced when you burn it, but 0.3, so we can see 50% of 0.2 is 0.1, and add that on, so that's why it's 50% more SO2, sulfur dioxide produced than burning. But obviously on the flip side, you can say that burning produces less sulfur dioxide, or that burning produces less mass solid residue, or putting the 10,000 plastic bags in the landfill produces less carbon dioxide. Next up, crude oil is a mixture of many different chemical compounds. The table shows information about 4 compounds that can be obtained from crude oil. So you've got decane, ethane, icosane and methane. Which compound in the table is a liquid at room temperature, which is 20 degrees? So if we have a look at them all, if its melting point is -30, then it will be a liquid, obviously, at 20 degrees. But at plus 174, this is where it becomes a gas. That's the boiling point. So the answer is decane, because ethene would obviously be a gas, because it's 20 degrees is hot enough to turn it into a gas. Obviously at 20 degrees it's not hot enough for icosane to turn into a liquid yet, and methane, it's too hot at 20 degrees, so it'd be a gas as well. So decane is the one. Which compound in the table has the highest viscosity, sorry. So viscosity is about thickness. So thickness is viscosity. Therefore, the longer the chain, the higher the viscosity. So icosane is the answer, which is here. The longer the chain, higher the viscosity. So higher the viscosity. Which compound can be used to produce a polymer? Ethene is used to produce polymers, because we turn the alkene, ethene, into polymer chains. The diagram shows the separation of crude oil in a fractionating column. explain how crude oil is separated into different fractions by fractional distillation. So firstly, we heat up the crude oil. The hydrocarbons vaporize, which means change into gas. So we heat up the crude oil, the hydrocarbons vaporize, the vapors enter the column here. So near the bottom. There's differences in temperature, so there's a temperature gradient in the actual fractionating column. So there's differences in temperature. So that means vapors with short chains, they actually condense higher up in the column. And that's because it is cooler at that point. So it's cooler up here. It's hotter down here near the heat source. So the vapors with the short chain condense higher up in the column, up at the top. Why do the vapors with the short chains condense higher up? It's because they have lower boiling points. So because they have lower boiling points, they condense higher up where it's cooler, so therefore the lower boiling point. And then on the flip side, vapors with longer chains, they actually have higher boiling points. And therefore, because they have higher boiling points, they condense back into liquids lower in the column. Where it's hotter. And that should get you your 6 marks. So just going back over it. You heat up the crude oil, the hydrocarbons vaporize, which is turned into a gas. The vapors enter the column near the bottom. There's a temperature gradient in the column. Then what happens is vapors with the short chains condense higher up the column where it's cooler because they have a lower boiling point, and the vapors with the longer chains, they have a higher boiling point, so they condense lower in the column where it's hotter. Next up, crude oil is a mixture of hydrocarbons. Name the 2 elements in a hydrocarbon. So name the 2 elements in a hydrocarbon. It gives you a clue in the name. Hydrogen, hydro, and carbon, hydrocarbon. From what was crude oil formed from? Crude oil actually comes from dead plants and animals, plankton is your answer. It doesn't come from acids, enzymes or metals. It's plankton, which is a plant. Figure 1 shows how crude oil is separated to produce different fuels. Okay, so it's just the fractionating column again. This time they've actually told you the different names of the hydrocarbons, the fractions. What is the name of this process? It's called fractional distillation. Why is the crude oil heated? It's to vaporize the hydrocarbons, turn them into a gas, so then they can condense at their various boiling points. The table below shows some properties of the fuels produced by the process. So we've got petrol, kerosene and diesel oil. Number of carbon atoms, you can see how it's increasing. Lowest boiling point, obviously that's increasing as you go down the fractions, and highest boiling point increasing again. So the next one, it's asking, oh, there's fuel oil as well, which is again longer. Which of the fuels has the largest boiling point range? So the largest boiling point range, so that goes from 370 to 600, 260 to 340, 180 to 260, 20 to 200. So the largest boiling point range, is fuel oil. Okay, with 240, the range there. And then plot the data for the diesel oil from the table on figure 2. So diesel oil, we've got 260 and 340. So 260 and 340 if you want to make a note there. So you can write down diesel oil. The lowest boiling point is obviously 260, which goes to 60, 70, 80, 90, 300. So it goes to here. And then the highest boiling point is 340, 10, 20, 30, 40, which goes to here. Good idea to use a ruler. Make sure you take up the same number of squares, 1, 2, 3, 4. And then there you go. And that's that. That'll get you 3 marks. So I hope you found that useful, and I hope you've done all right. Thanks for listening.